students, welcome to the video lecture series on Chemical Engineering Thermodynamics 2. I am Jamin Pandya, Assistant Professor in Chemical Engineering Department of LJIET Institute of Engineering and Technology. So let's continue with the chapter number 2, part 2, which is a solution thermodynamics application. So in this lecture, we are going to discuss about the composition dependency of liquid fugacity for species in binary solution. So question may be asked like from this topic is that prove Henry's law applies to species as a appropriate infinite dilute solution in binary solution, and Gibbs-Duhem equation ensure validity of Lewis-Randall rule for the other species as its approach purity. So can say that if I am going to apply Henry's law for any component for dilute solution in binary solution, the Gibbs-Duhem equation ensures validity of Lewis-Randall rule for other species and its appropriate purity. Okay. So when if I am going to apply for component point of Henry's law, then Gibbs-Duhem rule ensure validity of Lewis-Randall rule for the other component or for appropriate purity level. Okay. So I have to prove this statement. To prove this statement, let's consider Raoult's law or Lewis-Fugacity rule or Lewis-Randall rule, which are not possible to apply for entire concentration range. For very few mixtures, we cannot apply Raoult's law or Lewis-Randall rule. Are not possible for apply entire all concentration range because it is not possible all the solution behave ideally. Okay, so for very few mixture, Raoult's law or Lewis-Randall rule are conforming for all concentration range, or the very few substance which behave like near about ideally, so that we can apply the Raoult's law or Lewis-Randall rule for that particular component. A solution which does not obey the Raoult's law is known as a non-ideal solution, but even non-ideal solution behaves like ideally for some limited concentration range, where the fugacity is directly proportional to the concentration in liquid. For the concentration range where the Raoult's law and Lewis-Fugacity rule is not applicable, Henry's law is used. To understand this, let's consider one figure. Okay, so let's consider one figure in which we are going to draw the graph where fugacity versus mole composition, which is lies from 0 to 1. Fugacity, or can say that Hi, which is a Henry's constant. Okay, so fugacity on Henry's constant on y-axis and mole fraction is on x-axis. So behavior of Henry's constant that maybe look like this, which is starting from 0 to this Hi, Henry's constant, or can say Henry's law. Okay, so this is for the Henry's law. Now let's write for the this behavior is for the Fi, or can say that Pi, which is our Lewis-Randall rule or Lewis-Fugacity rule, or can say that Lewis-Raoult's law. Okay, now as I told you, not all the mixture or solution behave like ideally, so we cannot apply Raoult's law or Lewis-Fugacity rule to all solution, but some liquid or solution can say that behave like ideally for some concentration range, or can say that at initial concentration range. So if I am going to draw this dark line for initial concentration range, so it behave like this. Okay, first it behave like Henry's law, then after it behave like Lewis-Fugacity rule. So let here suppose there will be a 0.1, 0.2, 0.3, so it will be behave like ideally for 0.2 or initially mole of that particular component 1. So it becomes so on 0.4, 0.5, 0.6, 0.7, 0.8, 0.9 and 1. Okay, so this is how the graphical representation when we are going to say that some composition or some solution will be behave like ideally for some concentration range, or behave like Henry's law for some concentration range, and then after it follow the Lewis-Randall rule. So from the graph, from the graph, it's clear seen that the Henry's law is applicable for certain range of concentration. Because of that, Henry's law mostly used for the dilute solution. Henry's law and Lewis-Randall rule or Raoult's law are identical, but as a previous discussed, Henry's law obeys in solution by the solute at extremely low concentration. Normally, Henry's law used for the 0.01 to 0.02 mole fraction of the solute, or can say that dilute solution. When the Henry's law apply for the component 1 and very low concentration range of component 2 may be obeyed Raoult's law and Lewis fugacity rule, and it's clearly seen from this graph. So can Henry's law that can be given by YIP is equal to XI HI. Okay, here HI is a Henry's constant. Now we know that from Dalton's law YIP is equal to Pi bar. So using this equation, by replacing this, we will get Pi bar is equal to Xi into Hi. So we are just replacing this term with the Pi bar. Okay. Now Raoult's law that can be given by YIP is equal to Raoult's law that can be given by YIP is equal to Xi Pi saturated. So that can be written like this: Pi bar is equal to Xi Pi saturated. Okay. So if the pressure is replaced by the fugacity, this pressure is replaced by the fugacity, then this equation becomes like Fi bar is equal to Fi into Xi, which is known as a Lewis rule. Okay. So we know that Gibbs-Duhem equation that can be given by x1 in term of the fugacity that can be given by x1 into del ln f1 bar upon del x1 is equal to x2 into del ln f2 bar upon del x2. So it becomes our equation number 1. Now if we are going to rearrange this equation, we will get term like this: x1 del ln f1 bar upon del ln x1 is equal to x2 into del ln f2 bar upon, we are going to replace this x2 with x1. So if I want to replace this del x2 with del x1, then what I have to do? We know that x1 plus x2 is equal to 1. So can say that x2 is equal to 1 minus x1. So del x2 is equal to minus del x1. So if I am going to replace this del x2, so I have to put minus del x1. So I am going to put here minus del x1. Okay. So now taking x1 cancel out from both sides, so it becomes x1 del ln f1 bar is equal to minus x2 into del ln f2 bar. So let's suppose this is our equation number 2. Now rearranging this equation again, we can write d ln f2 bar is equal to, so we are just taking this x1 to this side, so it becomes minus x1 upon x2 into d ln f1 bar. Okay, so it becomes like this. Now again, if I am going to rearrange this equation, then it becomes d ln f2 bar is equal to minus x1 upon x2 d ln f1 bar. Okay, so this is our equation number 3. If the component 1 is obeys the Henry's law, then Henry's law for component 1 that can be given by, so if I am going to write if the component 1 is obeys the Henry's law, then for Henry's law for this component 1, that can be given by y1p is equal to x1 h1. Okay, we already studied the Henry's law in chapter number 1, so using this we can write here. Now we know that from Dalton's law yip is equal to pi bar, so I can directly replace this yip with pi bar, so it becomes pi bar is equal to x1 h1. Okay, so here is not I, it's a 1. Now so it becomes our equation number 5. Now equation 5 used for the ideal condition. If the pressure is replaced by the fugacity, then this can be given by f1 bar is equal to x1 h1. This becomes our equation number 6. Hence equation 6 used in this equation number 3. If we are going to use in this equation number 3, f1 bar is equal to x1 h1. Okay, so I am just putting the value of f1 bar here. So if we are going to put the value of this equation 6 in this equation number 3, we will get the value d ln f2 bar is equal to minus x1 upon x2 d ln h1 into x1. Okay, so again if we are going to represent or rearrange this equation, then it becomes d ln f2 bar is equal to minus x1 upon x2 into dx1 upon x1. Now if we are going to rearrange this equation again, so it becomes minus dx1, this x1 becomes cancelled upon x2. Okay, now if we are going to replace this dx1 with dx2, so it becomes dx2 upon x2, because we know that dx2 is equal to minus dx1. So if we are going to replace this dx1, so it becomes minus dx2. Okay, so it becomes look like this. So can say that d ln f2 bar is equal to d ln x2. So this becomes our equation. Now integrating above equation, we will get the ln f2 bar is equal to ln x2 plus c, where c is a constant of integration, where x2 is equal to 1. At that time f2 bar becomes f2 and c is equal to ln f2. Okay, so if I am taking a pure component of component 2, then f2 bar becomes fugacity and c becomes ln f2. Okay, how it becomes ln f2? If I am going to put the value of particular f2, then it becomes c is equal to ln f2. Okay, now again if we are going, so this above equation becomes like this ln. So let's considering this our equation number 7. So this equation number 7 is becomes like ln f2 bar is equal to ln x2 plus putting the value of c, which is ln f2. Okay, this becomes ln f2 here. So can say that ln f2 bar minus ln f2 is equal to ln x2. So can say that ln f2 bar upon f2 is equal to ln x2. Okay, now removing the ln, so it becomes f2 bar upon f2 is equal to x2. So f2 bar is equal to x2 into f2. So here we get the Lewis fugacity rule. Here we are starting from the component 1, which used for the Henry's law. We are applying Henry's law for component 1 and get the Lewis fugacity rule for component 2. So here we get Lewis fugacity rule or Lewis Center rule for the component 2. So this is how we can prove this derivation. So some students might question about how we can take c is equal to ln f2. Okay, so if I am going to take pure component, then this ln x2 becomes 1. Okay, so if x2 becomes 1, then ln1 becomes 0 ln1 becomes 0, so can say that c is equal to ln f2 bar, but x2 is equal to 1, so our f2 bar becomes f2, so it's replaced by the ln f2, so can say that c is equal to ln f2, and putting the value of that c when the component is pure, so we can change that in this constant of integration. So we are just changing the constant of integration and put the various value, we will get the Lewis-Randall rule for the component 2, or consider route flow in form of the fugacity. So this is how we can we can apply Henry's law and route flow for the component. So here by theoretically, if we are going to apply Henry's law, then after for component 2 we must have to apply this Lewis fugacity rule. So this is how we can prove that Henry's law apply for the species to appropriate infinite dilute solution, and give Duhem equation ensure validity of Lewis-Randall rule for the other species as its appropriate priority. So first we apply the this Henry's law, then using of the this Gibbs Duhem equation, we can say that the particular component which also follow Lewis fugacity rule. So this is all about today's lecture. I am completing my lecture here. Thank you.